let's do a nice example. Again, we already know the answer to this problem, but it's a nice example of how you calculate forces for straight and curved terms. So let's do this. Suppose I have a semicircle like so. And I have current going this way and then around the circle like so, a constant current. And I place this sort of semicircular wire in a magnetic field that points into the blackboard. Constant magnetic field pointing into the blackboard. Now we know this is a closed loop of wire, and so the answer has to be 0. The force on that wire has to be 0. But can we show that? And the way I would argue that we would do it is to take two terms separately. Let's look at the force on the straight wire first, and then let's look at the force on the loop of wire. So for the straight wire, I know that the force is very simply I times the length of wire, and let's say that this is going to be some length r. So the semicircle has a radius of r all around. IL times b. In this case, because it's a constant, it's going to be I times 2r for the length of this segment times b. And in that case, if the field is going into the board and the current is going left to right, the force on that would be upwards. Now let's look at the curved segment. For the curved segment, we have to be a little bit more careful. We can say that for the each increment of force I can write as ds cross b, and then if I want to find the total force for the curved segment, I have to integrate like so. That being the case, I can write this as I, the integral of I times ds times b times the sine of the angle, we'll call it theta, between ds and b. What we do then is to say, well, ds, I can write, if you remember your old formula about the length of segments, I can write that as r times d theta, and so my integral then becomes I times r times b times sine theta d theta, integrated between 0 and pi. And if I do that, I'm going to get, this integral will give me cosine theta times IRB integrated between 0 and pi. Actually, it's going to be a negative IRB cosine theta. When I put in my limits, I'm going to get a plus 2 IRB. But the direction of that force is going to be just the opposite. It's going to be, at this point, it's going to be upwards. And therefore, we're going to find that when I take this value and add it to this value, it's the same magnitude, but the direction is exactly the opposite. So when I add the two together, the sum of the forces then is just going to be 0, just as we would expect, as we know must be the case for a closed loop, magnetic field through a closed loop. This is a lot to take in, so take a breather if you need to. What we're going to do right now is work on the torque. If we can talk about forces, we can talk about torques as well. Suppose I have the following. Suppose I have a rectangular loop with sides A and B, and suppose I have it placed in a uniform magnetic field coming from left to right, like so. Let's calculate what the torque might be. First, let's look at the forces. So immediately we know the force on sides A are going to be 0. Why? If the current is going, let's say the current is going this way, in the case of this side and this side, the magnetic field and the current are parallel, therefore ds cross B is going to be 0. So the forces on the A sides will be 0. The forces on the B sides, though, will just be very simply, so the force on the close side, we'll call this side 1, F1, we'll call this F2. The force on side 1 will be equal to the force on side 2, at least in magnitude, and those will both be I times the length times the magnetic field, because the field and the current direction are going to be perpendicular. I cross B then would be 1, or I should say that the sine of the angle between them would be 1, and so it's just simply I times B, at least in magnitude. Of course, in this case, if the current is going upwards, the current is going upwards and the field is going this way, the force on this side is going to be into the board, so we'll call that F2, that's into the board. The force on F1 is going to be coming out of the board. And that's going to serve to rotate this loop in a clockwise direction, right? It's going to rotate this guy inwards, rotate this guy outwards, and so it's going, I should say, counterclockwise direction. If we remember our definition of torque, we can write as R cross F. So in this case, what's going on is our maximum torque, in this case, would be F1 times A over 2 plus F2 times A over 2, which would be I times A times B, using our expression for F1 and F2. And that would be our maximum torque. That is to say, when the radius or moment arm R and the force are at right angles to one another, we're going to have a maximum torque. Obviously, a minimum torque is going to be 0 when they're parallel to one another. So in general, we can say that the torque is equal to I times the area, and I'm going to write, if I treat A times B as an area, I can say that I can write my torque in this way. Oftentimes, we have characterized the product of a current and an area as a, in this case, magnetic dipole moment. And we use the Greek letter mu, that ubiquitous Greek letter, to indicate dipole moment. So the maximum torque would be mu times B. At the other end, if they were anti-parallel, we could write it as sort of a minimum, well, as minus mu times B. But in general, a more general expression would be that the torque is equal to the magnetic moment cross the magnetic field, or mu, magnitude of mu times the magnitude of B times the sine of the angle between the magnetic moment and the magnetic field. And so that's what we use in general. On the other hand, if we have n turns of wire, if I have multiple turns of wire, I can write the torque as n times mu cross B.
And this is the end of part 1. In just a moment, we will load part 2.